In this lesson, we are going to talk about the addition rule and complements for probability. So first here, two events are considered disjoint if they have no outcomes in common. And another name that we use for disjoint is mutually exclusive. And so notation for that is that means E intersect F, all right, upside down, U means intersect, is equal to the empty set. They have nothing in common. So sometimes we can visualize that using a Venn diagram. The rectangle represents the sample space, and each circle represents an event. For example, suppose we randomly select chips from a bag. Each chip in the bag is labeled 0 through 9. Let E represent the event, choose a number less than or equal to 2. And let F represent the event, choose a number greater than or equal to 8. These events are disjoint as shown in the figure. So here you can see this would be event E, a 0, 1, or a 2. Event F is an 8 or 9, and then the other numbers in the sample space not in either of the events is 3, 4, 5, 6, 7. So you can see they don't have anything in common. So if we were finding the probability of event E happening, there's 3 numbers out of the 10 total. If we're finding the probability of F, then there's 2 outcomes out of the 10 total. So the probability of E or F, we can simply just add together. All right, so our addition rule for disjoint events are mutually exclusive. So the probability of E or F is you take the probability of event E and add it to the probability of event F. Notation for this is a union symbol. Okay, so that is a union symbol. It means or. Okay. In addition to that, if you have multiple disjoint events, you can add more than 2 disjoint or mutually exclusive events. You just have to make sure all of them have no outcomes in common. All right, so in example 1 here, probability model shows the distribution of the number of rooms in housing units in the United States. First, verify that this is a probability model. Well, if you remember from our probability rules, it has to satisfy 2 conditions. 1, each probability has to be between 0 and 1. So if we look at all of the probabilities, they all are between 0 and 1, so it satisfies that. The other thing that needs to be satisfied is the sum of all of those probabilities needs to be 1. So if you add up all of those, you would get a total of 1. So it satisfies that. Since it satisfies both probability rules, then it's a probability model. Part B, what is the probability a randomly selected housing unit has 2 or 3 rooms? So we are finding the probability that a housing unit has 2 or 3 rooms. That would mean 2 union 3. This is, those 2 events are mutually exclusive because of a house that is a 2-bedroom house only cannot also be a 3-bedroom house. Okay, yes, a 3-bedroom house can have 2 bedrooms in it, but we don't classify it as a 2-bedroom house. We classify it as a 3-bedroom house because it has 3 bedrooms total. So to find that probability, since they are mutually exclusive, we take the probability of 2 rooms plus the probability of 3 rooms. And so that would be 0.032 plus 0.093. That would be 0.125. What is the probability a randomly selected housing unit has 1 or 2 or 3 rooms? So that's the probability of 1 union 2 union 3 rooms. So we just add the probabilities of each of them individually. So that would be 0.010 plus 0.032 plus 0.093. So that total probability would be 0.135. Okay, so mutually exclusive or disjoint events, meaning they don't have anything in common, we just add their probabilities together. Okay, so what happens when we need to compute the probability of two events that are not disjoint? All right, so back to our Venn diagram here. Suppose we're randomly selecting chips from the bag. Let E represent the event, choose an odd number, and let F represent the event, choose a number less than or equal to 4. So if you look at the Venn diagram here, you can notice they share the numbers 1 and 3. So both numbers 1 and 3 are part of both of those. So the intersection of those two events, what they have in common, is 1 and 3. So it's not the empty set. So these are not mutually exclusive and they're not disjoint. So what happens is we need to account for that overlap. Okay, so here you can notice you can't just add the two together. We have to account for what they have in common because you're counting them twice. If we find the probability of E and add it to the probability of F, we have counted the probability of this happening twice. So we need to account for that. So the general addition rule, and this is for any two events E and F, so we can use this at any time, is that the probability of E or F is equal to the probability of E plus the probability of F minus the probability of E and F. Okay, so just in different notation, the probability of E union F would be the probability of event E happening plus the probability of event F minus the probability of event E intersect F. All right, so example 2 here. If the probability of E is 0.32 and probability of F is 0.61, find the probability of E or F if the probability of E and F is 0.10. Okay, so notice there is a difference between or and. So just got to rewrite the formula. The probability of E union F is the probability of E plus the probability of F minus the probability of E intersect F. So we take 0.32, I'm just substituting in. Probability of F is 0.61 minus the overlap is 0.10. So we have a probability of 0.83. So now kind of same situation, but we're asked to find the probability of E or F if E and F are mutually exclusive. So that just means that the probability of E intersect F is equal to the empty set. So the probability of both of them happening at the same time is 0. So you can still use that general addition rule whether you have mutually exclusive events or not. And here's why. When we find the union, we would take 0.32 plus 0.61 and subtract the overlap, but the overlap is 0. So that would just be equal to 0.93. Okay. All right. Example 3 here, using the addition rule with contingency tables. These are also referred to as two-way tables, two-way frequency tables even. So what we have here, what this data is talking about, I guess, is marital status of those 15 years and older. So okay, marital status of those 15 years and older. So you have the number of males, number of females going down your columns, and then across your rows you have those never married, married, widowed, and divorced. So something we have to do with frequency tables is find the totals. So first thing we're going to want to do is find the total number of males. So if you add up all of the males together, you get 128, and that would be million. And if you add up all the females together, you get 135.6 million. You want to do the same thing with your rows. So if I add all those never married, 45.3 plus 40.1 is 85.4. If I add those married, it would be 137.8. Those widowed would be 14.9 million. And those divorced would be 25.5 million. So then the total amount of people we're talking about, if you add your total column, if you add the totals column and if you add the total row, you're going to get the same number, which is 263.6. So there's 263.6 million people in this report. So part A, determine the probability that a randomly selected U.S. resident 15 years and older is a male. So to find the probability of a male, we take the number of males and divide it by the number in the sample space. So number of males total is 128 million divided by the 263.6 million. We don't need to write out million because the millions are going to cancel. So that would be approximately 0.4856, which is 48.56%. Part B, determine the probability that a randomly selected U.S. resident 15 years and older is widowed. So now I'm looking at those widowed. So I go to all of those widowed. That's 14.9 out of, so you take the number that is widowed out of the number in the sample space. So that's 14.9 out of the 263.6, which is approximately 0.0565, which would be 5.65%. Okay, part C, determine the probability that the randomly selected person is widowed or divorced. Okay, so when we think of widow or divorced, that would be mutually exclusive because those can't happen simultaneously. Meaning when I choose someone, they can't both be widowed and divorced to the same person anyways. Okay, maybe they were once divorced and then they were married again and now they're widowed. Okay, but that would be two different situations. We're talking about, if someone was surveying you and they came and asked, are you married, widowed, divorced, or never married? You're only going to select one of those options. So since they're mutually exclusive, we just add their probabilities together. So the probability that you are widowed, union, divorced, because that means or, you're going to take the probability of being widowed plus the probability of being divorced. So that would be 14.9 out of the 263.6 for widowed, plus for divorce there's 25.5 million out of the 263.6. If you just add your numerators and then divide by the 263.6, you get approximately 0.1533, which would be 15.33%. Part D, we're finding the probability that the randomly selected person is male or widowed. Now this one is not mutually exclusive or disjoint because you could be a male and be widowed. So here's those males that are also widowed, the 3.5 million. So when we find the probability of being widowed or a male, we're going to take the probability of being widowed plus the probability of being a male and subtract the probability of being both a widow and a male. So probability of being a widow would be 14.9 out of the 263.6, plus the probability of being a male would be 128 out of the 263.6, and then minus those that are widowed males would be 3.5 out of the 263.6. If you add the numerators, that would be 139.4 divided by the 263.6, which is approximately 0.5288, which would be 52.88%. All right. And last bit here is the complement of event. So if S is the sample space of a probability experiment and let E denote the event, the complement of E is all outcomes in the sample space that are not outcomes in the event. So you might see this E to the C, or sometimes you might see E complement with a little apostrophe. Okay. So your complement rule, if E represents any event and E to the C represents the complement of E, then the probability of E complement would be 1 minus the probability of the event happening. Okay? So think of if our event is, if we're rolling a 6-sided die, and our event is to roll a 1, then that would be the set of the number 1, and the complement to that would be everything but a 1, which would be 2, 3, 4, 5, or 6. All right, so according to the American Vet Medical Association, 31.6% of American households own a dog. What is the probability that a randomly selected household does not own a dog? So the probability of not own a dog would be 1 minus the probability of owning a dog. So that would be 1 minus 0.316, which is 0.684, which would be 68.4%. Because remember, probabilities add up to 100%, and which those two do. And last example here, the data to the right represents the travel time to work for residents of Hartford County, Connecticut. What's the probability a randomly selected resident has a travel time of 90 or more minutes? Okay, well, first of all, these are mutually exclusive because there's no overlapping. So we need to know the total amount. If we added all those together, that would be 393,186. So the probability, let's do this first. Let's let E be the event. We commute 90 minutes or more. So the probability of E would be 4,895 divided by the 393,186. That's equal to 0.0124, which is 1.24%. Part B, compute the probability that the randomly selected resident will have a commute time less than 90 minutes. So less than 90 minutes would be all of these. So we could find the probability of each and add them together, but a quicker way is we're finding the probability of everything but what we just found. So we would take 1 minus 0.0124 to find the complement, which is 0.9876, which would be 98.76%. All right, so there is your addition rules with probability.